Hello, Professor. I'm here to introduce our project Enemy Face Detector based on transfer learning. First is introduction. Our project objective is to create a model that detects animation face in an image and provide a corresponding bounding box. But while we only use limited annotated animation data, especially seeing is less than 200. What is the motivation of our project? Animation is really popular, and animation industry is getting more and more important during the world. And there are many interesting applications of AI in animation, such as automating animation creation or content understanding. This project model is just the most basic task. It is the base of other tasks like animation content understanding. Most of these interesting applications are data-driven and require a lot of training data. But there is no large-scale animation face data set, so how can we make full use of existing dataset of all human face? Our answer is to create a model that animation face detection based on transfer learning that we can use for use of the human's data for this set. 2. Overall structure. This is the picture of our overall training and test structure process. For the train part, we will have real human face and animation face to do style alignment, transfer it into sketches, style, similar style, and do multitask training. To train the model to predict if there is a face or not, and to do bounding box regression. And in the test processing, we will do style alignment to the animation face and do selective search to get 16 for candidate bounding box and throw it into the multitask model, and to predict if there is a face or not and get the bounding box of the animation face. Data annotation. We collecting a dataset with 10,000 of animation face without annotating. We label this data with the tools label me, which including 7 points and 3 classic. If the face is more than 17%, we will label it as face, and if not, we will label it as no face. And if we cannot see the landmarks such as eyes of the face, we will label it as half face. And then we transfer it into a TXT file and import it into our model. And we will do augmented with these images like rotating and scaling. If the data is 70% similar to the original data, we'll label it as a positive label, and if not, we'll label it as negative label 0. And with this positive label, normalized bounding box, we will do our training based on it. Style alignment and selective search. As we know, real human face usually have quite different style from anime face. To better transform the model training on real human face to animation face, we want to bring their style closer, so we adopted a method in style alignment. In the style estimation method, we need to subdivide the test photo into a grid of non-overlapping. Then we can find the best matching photo patched from the photo sketch piles in the training set. Finally, we can obtain the target sketch patch from the corresponding sketch in the photo sketch pair containing the best matching photo match, or while getting inconsistent patch. Then, the final sketch is generated by combining the target style with content image, which can get from 2 previous steps. As we can see, the result is pretty good. After the style alignment transformation, we have similar style in the real human face and the animation face. Selective search. Selective search. In order to get the bounding box of a picture, we need to pick many rows from an input image, then pass rows to the model. We can use greedy search to do it, but it is really time consuming. So random search we can miss some objects, so we do the selective search. We capture the region of all scale that contains an object and merge the similar region, and then we get the region that contains the face of the animation character. The path we do selective search is like below. Training process. After doing the style alignment, we can see that the structure of the network. This is the PNet of MTCNN, and you can see that we output 2 results, which is face classification and bounding box regression. We do multi-text training here. We do face classification and bounding box regression at the same time with 2 different loss function. As we see, the total loss function is the binary cross entropy of face and the enduring loss of bounding box. Within the training schedule, we train 22 epochs of real human face dataset, and do transfer learning, train extra 10 epochs on annotation face dataset with fixed learning rate. When we do this combination, we can see that this method is mainly used because we want to get 2 kinds of photo. One is real human photos and another is anime face photos closer than before. And as we know, there are really huge difference between the 2 kinds of photo. And after the style alignment we mentioned before, it have similar properties, so we can train them together and save us from getting into troubles when we caused by the different brightness of photo or different colors of background. We can see the result that when we training only in the real human face, we have 93% of accuracy at negative and the 18% in the positive, and overall of 87%. And with the transfer learning, we can see the accuracy is have hugely improved in negative and slightly improvement in positive. So we can say that the transfer learning do improve the accuracy of training. and there's still a gap between performance on real human face and performance on anime face. And in the future work, we will try different style alignment method and try different CNN network and different network structure. For future work, we have a model that designed by ourselves. It contains two parts. One is a content extraction network that adopts a pre-trained VGG16 network in part to extract content feature, and then we can do training with two images as a pair. The image 1 comes from human face and the image 2 comes from animation face. We can have 10,000 of human face and 10 anime face, and it can combine with 100,000 pair. That can use very little data set to create a huge data set that can enable us to train the model. But because of the short of time, we cannot accomplish this model. We can do it after this semester. Thanks for your patience and listening. That's all of our project.